Let's get started again. Right, so the next lecture is on modeling value at risk. Anybody has heard about value at risk before? What is the definition of value at risk? Anyone can say it from your top of your head? Yeah.
Like the maximum possible losses you can have. Like you analyze, well, what is the maximum I can lose?
Yeah, or there is it's something to that effect. So it's got something to do with a probability of loss. So it's a quantile on your loss distribution, you know, for which there is a certain probability that you know, with there's a limited probability of how much more you can use, right? So let's get one step back and look at this distribution of profits and losses. So this is the distribution of returns. So what you see here in the middle, which is a deviation from the average return, this is what is called standard deviation. So far we've been working with the Markovich model that you've spent quite the first couple of sessions of this course on. The measure of risk was standard deviation, right? So that was how much we're going to deviate from the average. So that's one way of looking into risk. Now, value at risk is what is called a tail risk. And why do we call it a tail risk? Because it is not so much looking into a deviation from the average, but it's more concerned with what is happening in the tail of this distribution, right? So that's where the tail risk comes into the picture. And value at risk, as you said, this is, you know, a value, a loss number, an amount. Let's say a loss of 5%, for which, let's say, there is an alpha percent, a 5% probability of losing more. So there might be, you know, you might be losing more, but there's a limited probability for losing more than your value at risk, right? So this is what value at risk is. You can think of it as a quantile on your profit and loss distribution, on your return distribution, or on your loss distribution, for which there's a limited probability of losing more than that quantile, right? So this is what value at risk is. Then we have something called conditional value at risk. I'll get back to how we model that in the next lecture. But essentially, conditional value at risk deals with what comes after value at risk. So value at risk only looks at that quantile and says, well, this is the maximum I can lose with, let's say, a 95% probability. So there's still a 5% probability I can lose more, but I focus on, with this 95% probability, I'm not going to lose more than my value at risk. What conditional value at risk says is that if I am losing more than value at risk, then what is the average loss in the tail itself, right? So kind of VAR is cutting the tail, and conditional value at risk is actually just concerned with the tail which has been cut, if you like, the average value of the loss in the tail. And then, well, in the case of stress testing, essentially, you will be just looking into extreme scenarios, like the worst case, like what you already did. Some of you might have not. At question 7, essentially, that was about looking in the worst case. That was kind of a stress testing, what we did in the midterm project. Right? So this is the definition of value at risk. And this is how the model looks like. Right, so you might want to take some notes on what are the variables and what are the parameters of this model, and what is what are the positive variables and what are the free variables, because there are many things going on in this model. But this is a model for minimizing value at risk, and let's start with that. So value at risk here is defined as a free variable. So you want to minimize the value at risk of a model, of a portfolio. X is a decision variable, and that's a positive variable. So this is because we don't allow shorting. So some of your X's would be your budget. So you want to buy a portfolio based on the budget that you've got. And then here, essentially, you have another version of the fact that, well, we are minimizing risk and we are putting a limit on average return. So here I'm just saying that, well, the average return of the portfolio that we are buying has to be greater than some some target return, right? So let's say I have a budget of 100,000 krona, and then I say, well, if I want at least to get 2%, so I want in average to have a portfolio which the average return is greater than 2%, and then I want to minimize the risk at tail, the value at risk for that portfolio, right? So the rest of the model then is dealing with modeling the value at risk, essentially. So let's go through this like line by line. How do we actually both measure and optimize on value at risk? So the first step to do here is to define losses. So loss is also a decision variable. So budget is given, let's say 100,000 krona, it's a parameter, but loss is then is a decision variable which is dependent on the x value. So x is a positive decision variable. Loss could be both positive or negative. So this is just a free variable. And what is a negative loss? If my loss is minus 5%, that's a profit, right? So that's how loss is defined. So essentially what's happening here is that we are just turning, if you forget about the budget, which is just a number, it's a scalar, right? 100,000 or whatever. If it was 0, then it would be loss is equal negative of returns. This is essentially what it says, right? And now that we are shifting the whole thing by this amount by budget, right? So that would be loss compared to my initial budget. Yes? The L is the scenarios, yeah. I is the assets, and R in this case is this would be essentially 1 plus returns. 1 plus return here, right? Because we are comparing it with the budget. Right? And mu is the average return for a given asset. Right? So this one essentially is just saying, well, if I come with 100,000 krona, and then let's say in one of the scenarios, I end up with 98,000, I have a loss of 2,000, right? And the other way around, if I come with the 100,000 and I end up with 102, then I have I have 2,000 profit, which would be minus 2,000 in loss, right? So a positive value of loss is an actual loss, a negative value of loss would be my return, or my profit, right? So this is pretty straightforward. Then the next 3 ones together, they try to calculate value at risk. And how does that work? So I have a decision variable here, which is called value at risk deviation. And value at risk deviation, note that down. This is a positive, it's important that it's a positive variable. So this is a positive variable. So in the cases where loss is greater than value at risk, if I have a loss which is greater than value at risk, and value at risk itself is a free variable. So we have 3 variables here. So if loss is greater than value at risk, then I have a deviation to the right of my value at risk, and I want to save that into this positive variable. So whenever I have a greater loss than value at risk, I want to save that value. If the loss is smaller than value at risk, so I am to the left of my value at risk, then I get a negative number, but this is a positive variable, so the value of that would be just 0. So notice here, if I want to draw the density function for losses, so now these are the probabilities. Probability, and these are losses. So this is my value at risk, right? Because the greater loss, if I have, this is distribution of losses, so value at risk would be my right, cutting the right tail, right? If I want to minimize the loss, that's why I want to look into the losses rather than looking into returns. And I want to minimize, I want to have this value at risk to be as small as possible. I want to bring it as much as possible to the left. But I mean, there's limits to how much it can come to the left, because at the same time I want to maximize my return. So in one way I want to push the average to the right, but normally when I want to push the average to the right, value at risk also kind of moves further to the right, so there's limits to how much I can push value at risk to the left. I mean, ideally I wanted to do this, that I want to bring my average return as much as possible to the right, while I'm bringing value at risk as much to the left, right? And that's well, there's an inherent conflict in that, right? Because these two kind of follow. Risk, and the more risk, the more return, as we know in financial markets. So you have to take some more risk to get some more average return. So the natural consequence is the more you're moving the average to the right, the more this guy would also go to the right. So the thing is, find the portfolio for which you can go as much as possible to the right for the average without your value at risk shift as much as the alternative portfolios. Essentially, that's the idea of this model, right? But what is happening then, particularly with this value at risk deviation, that variable, the scenarios which represent this area. So this area is where we are to the right of value at risk. So if I'm here, then I have a portfolio, I have a loss, which is greater than this value of var. So all the values, all the losses, all the scenarios representing this tail to the right of value at risk, they have loss values greater than value at risk. Those values are saved into var dev, into this variable, right? And if loss is to the left of value at risk, then I get a negative number, and then the var deviation would be just 0, right? So again, I'm only concerned with the tail to the right of value at risk. Yes?
You're speaking of the average loss, or?
It's not. I'm not looking at the average loss just yet. That would be the conditional value at risk model. Here, I'm only interested in the scenarios, individual scenarios, that have a loss which is greater than value at risk. And the value of that deviation is saved into this variable. Note this variable has an index L. So for all the scenarios I have to save the value. How much do I deviate? If I have a positive deviation from value at risk, I want to save it there. If I have a negative deviation from var, I just want to put a value of 0 there. I'm only concerned with values in excess of var. And the reason why I'm interested in that is that I want to make sure that whenever there is a loss in excess of var, I get a positive number in this one, right, in var dev. And then I have a binary variable I call ZL here. I want that ZL, that's a flag indicating that I have a scenario where the loss is in excess of var. So if this guy is positive, var dev is positive, and this is just a big number. This is just a big scalar, a big M. For those of you who have the integer programming course, it's a big M constant. It's just a big enough number to make sure that this inequality will hold true by putting z equal to 1 when var dev is positive. So the value has to be just big enough that it's always bigger than whatever amount of deviation possible you can get. So you don't have to make it too big, just big enough that you don't cut some of the solutions. Right, so what happens here is that if this value is positive, then this one should be 1, right? Otherwise, you will have 0 greater than the positive number, which is not true. So as soon as you have a deviation to the right of var, then there will be a flag which has to become 1. We don't care about the zeros, right? Because if this guy is 0, then this could be 0 or 1. But obviously, because of the fact that I mentioned here, that we want to bring value at risk as much to the left as possible, right? And there is we want at the same time we're maximizing for return. So as we are maximizing for return, it's the scarce resource, if you like, are those variables which are to the right of value at risk. So we want to have as few ones as possible, because that's the way we can maximize our value at risk. Yes?
Why don't we combine the two constraints, the losses minus var? Why don't we say highest loss times z is larger or equal to losses minus var? Wouldn't that have the same effect?
Not really, because the idea is here that you want to cut off all the minuses. And if you did that, then you will have also the negatives as well. The whole point is that you want to do is asymmetric. So the reason, if you just put loss minus var, notice here this is greater or equal. This is not equal.
Yes.
So if you put these two guys instead of this,
yeah,
right, then there would be all those cases that you have negative values,
yeah,
would also come in. Whereas we want zeros for those, right? So that's the impact of the var dev. Right, so here here because of what we are doing, we are minimizing value at risk. We are sure to have that the model has an interest to have as few ones as possible. This is our scary source. And we are saying that, well, we have an alpha. We said that there is a 5%, let's say, probability that we are going to get a loss greater than value at risk. And if we had 100 scenarios, then let's say, then what does it mean? That means that we allow only for 5 of the scenarios we have a loss which is greater than value at risk. So what does that mean then? It means that our alpha is a 95%, so this would be 0.95. Here we have 1 minus a probability of, let's say, if we had 100 scenarios, would be 1 over 100. And if you have 5 of these z's which become positive, so you have 5, we allow for 5 scenarios to have values greater than value at risk. So 5, if you're summing those 5 guys, 5 multiplied by 100, that's 5%, right? 500. So 1 minus 0.05 would be exactly greater or equal 0.95, right? So this last equation makes sure that you get the probability right. So you're allowing, we are counting how many scenarios for which we access var, and this one is the probability that that we don't lose more than var, right? This is the 95% probability that we don't lose more than var, and the PL is just the probability of the individual scenarios. No. So there are 2 different things. So PL has got to do with number of scenarios, or let's say if I had 1,000 scenarios, that PL would be just 1,000. So that if they are equally weighted scenarios. So this was just an example of saying if I had 100 scenarios, then let's say, and the probability of each scenario is 100th, let's say. So then just to make this calculation easy, then I would allow to have 5 scenarios for which I can access var. I have losses in excess of var if my probability was 95%. But then the probability could be, if my probability was 99%, then I would just allow 1 scenario for which I'll have a loss more than var. On the other hand, if I had 1,000 scenarios and I had a 99% probability for my var, if I have a 99% value at risk I'm looking at, then with 1,000 scenarios, equally probabilities, then I can have 10 scenarios that can have a value of 1, right? So this is how it works.
So alpha is directly linked to how many scenarios you want to...
No, alpha has got something to do with the area under this density function to the left of value at risk. So this is my alpha. This is my, let's say it is 95%. So this part here, then this is 1 minus alpha, which in this case, let's say is 5%, right? So alpha is just a kind of the confidence level that they choose for the quantile, right? So this var is a quantile. This is, in this case, var is a 95% quantile of this loss density function. So, and normally what you would use is either 90%, 95%, or 99%. So this is just to make sure that you have, with big enough probability, you are not going to lose more than a certain amount. That's the function of alpha. So alpha's got nothing to do with the number of scenarios or anything. It's got to do with your perception of how much you're going to allow in terms of probability, how much you're going to allow, what is the probability of losing more than your value at risk, right? So you just decide on alpha. And then normally you decide on something bigger than 90%, right? So that's alpha. But then scenarios is about, you have this distribution, but scenarios is about approximating this distribution with some scenarios, right? So you have some distribution. Let's say you have some true distribution. We don't know what that is, but we can approximate that with generating some, random scenarios based on historical data, or based on some other methodology. But you can generate as many scenarios as you like. So the more scenarios you generate, hopefully the finer you can approximate the true underlying uncertainty distribution set, right?
This probability would always be a bell curve. Is that
No, that's not. And it's actually in many cases it wouldn't be. You might have You might have long tails, or kind of you can have biased curves, or you can have fat tails, as they're also called. Long biased, or you can have fat tails. So there's not. So the assumption of normality is definitely not always fulfilled when you're looking into the returns of financial markets. Any other questions to the value at risk model? Yeah.
So can you just explain the ZL?
The ZL.
Yeah, it's the number of the.
So yeah. So ZL is a binary variable. So it's a binary variable. It can only have the value 0 or 1. And it would be set, the value of this would be set to 1 whenever you are in one of those scenarios where you have a value at risk, when you have a loss in excess of your value at risk. So that's the only purpose it has. It's counting how many scenarios for, or it's a flag saying for which scenario we have a loss which is in excess of VAR, which is our value at risk. Right? All right. But as I said, you get the chance to work with these models, and then you're going to get back to it, and then after you have some hands-on with this, then you will probably generate more questions, and we can get more in depth with understanding of the model, or your understanding of the concept in general. All right, let's take a short break this time, and we will start 2 with the final lecture on conditional value at risk.